Welcome back to Elements of Chemistry tutorials. In this video, we're going to talk about the quantum model of the atom and how to determine quantum numbers. There are three people you need to understand: Wolfgang Pauli, Werner Heisenberg, and Erwin Schrödinger. And they all were in the mid-1920s. Okay, so Pauli first. He said that no two electrons can exist in the same state simultaneously. We call it the Pauli exclusion principle. No two electrons can be described in exactly the same way. And this explains a lot about the arrangement of the periodic table. Werner Heisenberg, right on his tails, built on the work of Pauli and Bohr, and he stated that we can't precisely know the position or momentum of an electron or photon without changing said position or momentum. So anything we did to determine its speed is going to change its position, and anything we do to determine its position is going to change its speed. So that's the Heisenberg uncertainty principle. Erwin Schrödinger, fabulous mathematician. He built on the work of Pauli and Heisenberg, and I mean months. These are like months within each other. He took the atomic model one step further and developed the quantum mechanical model of the atom. So he treats the model, or the electrons in the atom, as matter waves surrounding the nucleus. In the quantum model, electrons exist in fuzzy probability clouds where we can predict the likelihood of finding an electron, but we can't determine its actual position because of the Heisenberg uncertainty principle. So these fuzzy clouds are centered around the nucleus in energy levels n. And within these energy levels, the electrons exist in sublevels of different shapes. That's called the angular momentum quantum number L. And within these sublevels, electrons exist in specific orbitals of different orientations on the XYZ axis. That's the magnetic quantum number m sub L. And within the orbitals, there are two electrons, and each of those electrons have opposite spin, the spin quantum number m sub s. So one is spinning clockwise, the other is spinning counterclockwise. How do we know all of this? Lots and lots of math. But let's just jump and talk about how to use these things, okay? So first of all, a specific quantum number can be identified by four sets of numbers. N, and we're going to use this blank periodic table to try to explain it to you. So N is the energy levels. So we're going to number our periodic table 1, 2, 3, 4, 5, 6, 7. And we know we've completed the seventh row and eighth is going to start soon. Okay, so if we were saying this element right here, its N would be 2. And this element right here, its N would be 4. This element over here, its N would be 1. So that's our first quantum number. Pretty easy. So let me get those dots out of here. And let's talk about m sub L. We also refer to those as blocks. Now, our L can have values of n minus 1. So these guys here, and we're going to use this one right here, all have L equals 0 for their second number. So if we're doing this element right here, its first number would be 2, its second number would be 0. Okay, so if that's 0, L equals 1 is this set over here. We sometimes refer to these as blocks, especially when we start to do electron configuration. So this set of the periodic table, all of these have an L equals 1. Now let's think about this. Angular quantum numbers have n minus 1. Because the first energy level, we can only have 0. 1 minus 1 is 0. Every energy level is going to have that L equals 0. But it doesn't start until the second energy level that you get an L equals 1. So let's talk about this element right here. Its N would be 2, its L would be 1. If we were doing this one right here, its N would be 6, its L would be 0. Okay, moving on. These transition metals here, they're all going to be L equals 2. So let's look at this element right here. Its second quantum number would be L equals 2. Okay, now this is the one that gets people. The magnetic quantum number. It's negative L going to 0 to positive L. Identifies orbitals. Look at orbitals. This orbital's name is 0. That orbital's name is 0. I'm going to do over here. Clean that L equals 1 out. So I have some room. Okay, here L equals 1. Let me put that back in. I'll put it up here. Change different pens. So L equals 1. This orbital, negative L. So this is going to be a negative 1, 0, 1, negative 1, 0, 1. They repeat. Okay. So if L equals 2, these orbitals are going to have to be negative 2 going through to 0. So negative 2, negative 1, 0, 1, 2, negative 2, negative 1, 0, 1, 2. So let's do this element. We'll go back here. Its N would be 2, because it's in the second energy level. Its L would be 1. Its orbital would be 1. If I were going to do this one right here, put it as a 0. Its N would be 3. Its L would be negative 1. Oops, excuse me. I almost messed that up. Its L would be 1 because its L equals 1, but its orbital would be negative 1. Okay, now we have the last quantum number, and that's the spin. Electrons enter an orbital, clockwise spin first. So we're going to spin clockwise, which we show as an up arrow, and then counterclockwise as a down arrow, and that completes the orbital. We have to put one electron in each orbital before we can pair them up. So we're going to go up, 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 and then down, down, down. Clockwise, 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 counterclockwise, counterclockwise, counterclockwise. So yes, this element and this element, those electrons are sharing an orbital, but they're of different spins. So let's just pick one and figure out its complete set of quantum numbers. Let's do this one right here. I'm going to highlight it. So for that one, we're going to put it over here so we can have it highlighted. Its quantum numbers are going to be, it's an energy level 3. It is in an L of 1. Now we look at its orbital. Its orbital is 1, and it's a counterclockwise spin, so it's minus 1/2. And that's the 4 quantum numbers. If we were going to do this element, let's do this one right here. Its N would be 2. Its L would be 1. Its orbital is 0. And it's going to have a clockwise spin because it's the first one going in. So it'd be 1/2. You don't always have to designate a positive, but you always have to designate the negative. So elements are usually described by their last quantum number, but realize it's going to have all the electrons that come before it. So if we were going to do helium, helium is, let me highlight this in a different color so you can see it. This is helium right here. Helium is going to have 2 quantum numbers because it has 2 electrons. The first one is going to be 1, 0, orbital 0, and this is going to be a negative, positive, I'll put the positive sign, 1/2. Its second one, this is going to be a downward spinning electron, 1, 0, 0, negative 1/2. Those would be the 2 quantum numbers for helium. If we wanted to go ahead and add the one that goes right here, so that's lithium. To do lithium, it would have helium's quantum numbers, and its own unique last one, which would be 2, 0, 0, 1/2. And elements are described by their last unique quantum number. So let's try some. What is the quantum set of quantum numbers used to describe the last electron in carbon? Well, we're going to have to go to our periodic table and find carbon. Carbon is element number 6. So 1, 2, 3, 4, 5, 6. So that was the one that we already did. That's the 2, 0, 2, 1, 0, 1/2. Its N was 2. Its L is 1. It's in the second one in, so its orbital is 0. And it's the first time you're going into that orbital, so it's a positive 1/2. Which element will have these quantum numbers? 1, 0, 0, 1/2, and 1, 0, 0, negative 1/2. Oops, we answered that one. That was helium. We use that as one of our examples. Which element is described by the final quantum number 2, 1, negative 1, negative 1/2? Okay, so let's think about that. Energy level 2, 1, negative 1, negative 1/2. That's going to be this element right here. And if we look at a periodic table, that happens to be oxygen. Okay, now your turn. Take a few minutes and try a couple of these. Okay, hopefully you're back. Let's talk about copper. Copper, if we go up to our blank table, is right here. So that would be in a 4, 2, because its N was 4, its L was 2. It is in a 1 orbital, and it's the second time you're going into that orbital, so it's a negative 1/2. That pen needs a new tip, I think. There we go. 4, 2, 1, negative 1/2. Okay, let's look at number 2. Is 1, 1, 1, 1/2 an acceptable quantum sequence? Why or why not? Well, it's not, because in the first energy level, that second number has to be n. If that's n, that's got to be n minus 1. And 1 minus 1 can't be 1. The first energy level only has zeros. List all the quantum numbers in the element boron. So we look at boron, that's element number 5. We're going to have to do a lot. We're going to have the hydrogen 1, 0, 0, 1/2. Helium 1, 0, 0, minus 1/2. We're going to have the 2, 0, 0, 1/2. The 2, 0, 0, minus 1/2. That's 4. And then the next one that comes in is going to be 2, 1, because our L is 1. And now the first spot is a negative 1, because remember that range is negative L going through to positive L. And it's the first electron going into that orbital, so it's a positive 1/2. And those would be the 5 quantum numbers for boron. I hope this video gave you a quick little introduction to quantum numbers and identifying quantum numbers. I hope you've had a good day. Have a great tomorrow. Stay safe, be kind, and come back and let me know if you have any questions or comments. Have a wonderful day.